Good afternoon, everyone. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and welcome to the Australian Institute of Physics Theoretical Physics Seminar Series for 2022. As usual, I'd like to start by acknowledging the people of the Ngunnawal Nation, the traditional custodians of lands upon which ANU now stands, and indeed all of Canberra. And of course, we acknowledge the traditional custodians of lands all around Australia. We pay our respects to their elders, past, present, and emerging. In the last seminar, we heard from Professor Srubhati Goswami, who talked about some of the latest developments and challenges in neutrino physics. It was a very interesting talk. And if I recommend it to you if you missed it and you're interested in fundamental aspects of nuclear physics. All of the talks from this year and indeed from last year are available on the AIP YouTube channel. Just do a search on AIP YouTube and you'll see them all there. And you can catch up on anything you miss. Today's talk is on time crystals, which were first proposed to exist by Frank Wilczek in, I believe, in 2012, and basically are physical systems for which the lowest energy state is not necessarily an equilibrium state, in the sense that the state is characterized by properties which are not independent of time, and further which exhibit some repetition in time. The system then can't come to rest because it's already in its ground state. And these systems break continuous time symmetry, although they have a type of discrete time symmetry. The term time crystal arises because of the analogy between a periodic distribution in time, in the case of a time crystal, and the periodic distribution of atoms in space, for example, forming a traditional crystal lattice. And the existence of time crystals has now been demonstrated experimentally, using a number of approaches, at least one of which I'm aware of is a macroscopic system, ferromagnetic macroscopic system. But in addition to the implications that time crystals have for our understanding of some of the properties of even the simplest quantum systems, there are also interesting and very important potential applications in fields such as quantum computing and metrology, just to name a few. So to explain a lot more about this fascinating emerging topic, today's seminar is being given by Dr. Stephan Rachel from the School of Physics at the University of Melbourne. Stephan's talk today is entitled Realization of a Discrete Time Crystal on IBM's Quantum Computer. Thanks, Stephan. Over to you.
Okay. Yeah, thanks very much, David, for the kind introduction, and thanks, Murray, for inviting me, for having me. Let's jump right into it. The outline of my talk is as follows. I will give a not too short introduction about why time crystals, what are time crystals, where to put this in which area of physics, and this is not very technical, of course. I will then spend a little time to kind of discuss the so-called first generation of experiments, which kind of were kind of done about 5 years ago, and will then come, for reasons we'll see, to kind of the main part of this talk, where explain how we simulated or realized time crystals on a quantum computer. And for that purpose, I have a short part about quantum computing. It's really it's very simple, but the idea is for those who have never really done anything with a quantum computer or don't know how it works. It's meant to be like, if you have some basic physics knowledge, you'll understand how we use a quantum computer and how it works. And then eventually we'll talk about the main part of this talk is about our work on time crystals on IBM's quantum computer. Okay, to begin with, and I think after the introductory words by David, it's clear that this time crystal is not about some magic crystal ball or like Marvel's infinity stones, but it's really a solid physics system. Okay, so let me start with something probably most of you know or have heard about, namely the perpetuum mobile. And so that is an isolated machine which keeps in motion indefinitely. And of course, that is something people have thought about for a long time. I think it started probably at least 900 years ago. And of course, inventors try to come up with something which would come in very handy, of course. So here's an example on the right. This is the so-called water screw by Robert Flood. I found this on the internet. There are other famous examples of so-called or machines which were supposed to be perpetuum mobiles, although we know, of course, as we learn in probably already in high school, that such a machine cannot exist. But nevertheless, let's think about for a second what it would take to build a perpetuum mobile. And essentially, there are two requirements. The first one is we need a source of energy to oppose dissipation, or have any other mechanism to avoid dissipation. Okay, it might be technical. The discussion might be debatable if that's possible or not, but at least that's something you have to do. The second requirement is far more challenging, namely you have to avoid the second law of thermodynamics, which tells us that a system always evolves into its maximum equilibrium, its maximum entropy state. Okay, now as said, so that there is no perpetuum mobile, and I think in the 18th century, the serious scientists realized that, and then essentially these ideas and inventions stopped, and only few people kept trying this. But I think it's kind of a long time is established that there's no perpetuum mobile. Now, okay, nevertheless, let's ask the following question. Let's suppose we had a frictionless system. For whatever reasons, we were able to have that, no friction. Now we think of a physical pendulum, and we kind of give it a push. It starts oscillating. The question is, would it keep oscillating indefinitely? Okay, and in fact, there is one answer to that question, which is yes, that is possible, but only if it was described by a single degree of freedom. Okay, then this would indeed keep oscillating indefinitely. Of course, you know that this can't be, and the reason why this can't be is that a physical pendulum, of course, is not 1 degree of freedom, but it consists of atoms, of molecules, of many, many particles. And as it happens, the oscillatory motion, due to acceleration and so, some of the energy will leak out of this kind of center of mass motion and will leak into internal degrees of freedom, such as atoms or any other parts in the solid in this kind of pendulum. And then they will start kind of moving. And what is happening is that essentially the pendulum will heat up and it will reduce its motion. Okay, and eventually it will stop. If the pendulum is very rigid, it might take a long time, but it definitely kind of stops. So that is kind of how this works. Okay. All right. We already heard about time crystals, and they were invented by Frank Wilczek. Frank Wilczek is, I guess, it's well known to everyone, Nobel laureate, and he did this fantastic work as a PhD student about asymptotic freedom. But he's also very well known for his work in condensed matter physics. So not everyone might know he spent in his later years a considerable time on fraction quantum Hall effect, anyons, fractional statistics, high temperature superconductivity, and so on. And in 2012, he had this idea of a ground state time crystal. And he already mentions in the paper that this comes dangerously close to a perpetuum mobile. So some people even say Wilczek just formulated the idea of a perpetuum mobile in the modern physics language of symmetry breaking. Now, what he proposed was that it's possible to have time translation symmetry breaking, and that would lead to such a ground state time crystal. So very briefly, let me try to explain to you what he had in mind. So what you see here is a superconducting ring. Okay, and a superconducting ring, if you thread a flux through it, which is not a multiple or not a flux quantum, unit flux quantum, but a fraction of that. And if you kind of pierce this flux through the ring, you will kind of start a persistent current, a superconducting current or a supercurrent, which keeps going in principle for indefinitely. Okay, of course, such a supercurrent does not break time translation symmetry. Okay, so if you kind of shift this in time, it will behave the same way. Now, Wilczek's idea was that in addition to that, he needs some attractive potential between the particles in the ring, let's call them the ring particles. And if there's an attraction, of course, this homogeneous distribution of the charged particles will kind of be destroyed. And then you will have some accumulation of these particles, maybe something we might call in the modern language charge density wave. But in any ways, it's not homogeneous anymore. And this kind of inhomogeneity in the spatial distribution in the ring will then lead to time translation breaking, because now, of course, it makes a difference for this kind of supercurrents, whether you have like maximum minima of the charge distribution. Okay, so that was roughly Wilczek's idea, and if you think about it, it's rather clever. And he kind of gave several ideas and further insights and calculated stuff. So if you read this first, it's really an amazing work. Yeah, so bottom line, if you would summarize this in one sentence, it's a charge density wave on top of a persistent supercurrent. And that would give something like an AC supercurrent, and that would be, of course, something which violates time translation symmetry, would be time translation symmetry breaking. Okay, let me emphasize that for those of you who know about spontaneous symmetry breaking, you would say, oh, it's another symmetry breaking, that's boring, but that is not the case. So time translation symmetry breaking is actually very different. And one way to see it is by just looking at the generators. If you have a space crystal, so you break space translation symmetry, the generators are momentum, right? And momentum is very generic, system independent. However, the generators of time translation, that's of course Hamiltonian. If you do time evolution, you have the exponential of the I times Hamiltonian times time. So the generators are the Hamiltonian. That's of course the most system-specific object you can have. Okay, you see, time translation symmetry is very different from other symmetries we know. Okay. Now, Wilczek's idea, unfortunately, was shortly after proven or claimed to be wrong. It was first Bruno, and then shortly after Nozier. And they kind of worked out, like on a physics level, some proofs that this couldn't work for a ground state, that this would not be possible, that such a system would be stable. And then, like a year later, it was Watanabe and Oshikawa, and they formulated actually a strict no-go theorem, proving that this is impossible. So ground state time crystal cannot exist. And essentially, that is based on some analysis of correlation functions. Okay, so it seems with that slide, my talk could end and time crystals are not possible. I mean, it's kind of some coincidence that about the same time, the research on what is called many-body localization started, and people realized that there might be a mechanism to get time crystals after all, although in a very different sense than Wilczek envisioned. So before we get there, we need to kind of discuss a few other things. And the first one is what is thermalization. So thermalization usually means that system is coupled to the external bath. That means there's a reservoir for conserved charges, for instance, energy or particles. And that's what we kind of, or what is often taught in statistical physics 101. That means then over time, such a system ergodically explores all the microslaves which are available and reaches thermal equilibrium, like a Gibbs state. Okay, and in particular, the initial memory is lost. The initial details don't matter anymore because the long-time behavior of the system is just described by something like the temperature and pressure, but all the microscopic details are lost. So initial memory is lost. Okay. Now, of course, if I say I couple to an external bath, by definition, I do not have a closed system. Okay, so the question is, if I consider a closed system, how does thermalization actually work? And of course, there's a technical answer, which I'm not gonna offer you. But the way to think about it is maybe a helpful way to think about it is to reformulate the word thermalization and consider it equivalent to the spreading of quantum information over highly non-local degrees of freedom. Okay, so that means what is happening is that essentially, okay, maybe a hand-waving way of saying it is that the system itself serves as a bath for the system, and in that sense, this initial information can be hidden in non-local variables such that you can't access it anymore if you calculate expectation values of local observables. So in that sense, the system has a very tricky way of hiding the information that is not accessible anymore. And then the end result looks exactly the same as before, that you reach like a long times a thermal equilibrium state. Okay, so again, if you ask someone, if you wonder how does thermalization work in a closed system, the system itself somehow acts as a bath. Okay. Now let me emphasize that thermalization is really the expected outcome in a generic many-body system when you have only a few conservation laws. So after long times, you would always expect that the system thermalizes. And let me emphasize here the words generic and many-body. What I mean with that is the following. Well, many-body, of course, means it's an interacting many-body system. So I cannot have only one or two particles. I need many particles. Of course, the physicists never specify what we mean with many, but let's say 2 or 3 is not many. And interacting really means that I need some electron-electron interactions or something comparable. Because if I had a non-interacting system, a free fermionic system, it was integrable. And that is exactly what I mean also with generic. Generic means that it's not integrable, because integrability would lead to infinitely many conserved quantities, and then there's a way of avoiding thermalization. But we'll kind of see this, we'll come back to this later. Okay, so generic system has only a few conservation laws, and then thermalization is the expected outcome. Okay, now I want to briefly show you, it's a very simple calculation. It's like a back on the envelope back of the envelope calculation. I would like to show you that you always what you can expect for real-time dynamics. And what we do is the following: we simply oh, here's a question, and the question is that is thermalization require entanglement? That is actually a good question, because I forgot to say it. A more modern way of saying thermalization is that the system becomes entangled or becomes highly entangled. If it's now a necessarily required entanglement, I'm not sure if this is just a broad, simple question, or if there's some you know, some details hidden behind the question. So maybe come back to this later. But yeah, so normally in a standard sense, we mean with thermalization, the system becomes entangled. Okay, so let me come back to here, this real-time dynamics. Now, we consider a state, a wave function, time t, and this is simply, we can write this in an eigenbasis of Hamiltonian, and E nu are the eigenenergies and nu are the eigenstates. And then, of course, essentially time evolved state could be expressed as shown here in this equation. Okay. Now, let's consider an arbitrary expectation value of a local operator, which is called O. And if you simply plug in this definition, what you get is this expression here. Okay, this is really like second week of Quantum Mechanics 101. And now what we're going to do now in the following is we kind of split this sum into two parts. The first part contains only those matrix elements or the states which have the same energy, where E nu is identical to E mu, so they are degenerate. And then in the rest of the sum, the second sum, all other terms are contained. So in other words, here clearly the time dependence drops out because this difference is 0, and here we have this term. Okay, now let's kind of analyze this. You see, it's very simple, but we can already kind of see the essence of thermalization. Namely, the following is happening. So here. This is obviously not, this is time independent, and this term is time dependent. And if we assume that the spectrum is not symmetric, it's rather, you know, kind of has not a particular shape, just a generic spectrum, we can't expect that this kind of cancels out symmetrically. But what is happening instead, if the particle number is large, meaning that we have many states, many terms which are contributing, then there's a mechanism called dephasing, which kind of means that this term kind of dephases, which means these phases become very small, and essentially this term can be neglected. There's still small fluctuations, but this term becomes almost negligible compared to that one. Okay, so what is then left is essentially this. That's what people sometimes calls diagonal ensemble, and that is exactly the state that it we equilibrate to a time-independent late-time steady state. Okay, so what was the key here? The key was that we assume a large particle number, as I emphasized before, many body. We see immediately if I had few body system, just a few particles, then there was no reason to assume that this term becomes small, that there's dephasing. And as a matter of fact, there's something some of you might know. Whenever you study a small time system, you kind of look for the time dependence. You see that there might be oscillations like revivals and stuff like that. You know, so this is very generic. Where a few many body system shows a non-trivial time dependence. or shows a time dependence at all, which doesn't go away for late times. So that's why we need many particles. Yeah, okay, let's move on. I mentioned before at the end of the slide about Wilczek's original idea that it was about the same time when people started to become interested or very interested in many-body localization. So it's a completely different topic. So let me very briefly mention a few key points about this. So we're interested in many-body localization because it's a principle, it's one of the key, or it's the key mechanism for limiting or avoiding energy absorption, and which you would otherwise expect in driven systems. Now, this all goes back essentially already to Anderson himself. In his famous localization paper, he already mentions that if you consider this disorder problem and you have many body interactions, then there is something like in analogy to Anderson localization. So usually when we have non-interacting system, we talk about Anderson localization. If it's a many-body interacting system, we talk about many-body localization. But it essentially was already envisioned by Anderson himself. And then you see here these kind of first few papers who kind of address this difficult problem. And then after 2010, it became more mainstream and people kind of became very active in this field. Now, maybe the most important part about many-body localization is that these are systems which cannot act as a bath for themselves. So this kind of idea of thermalization in a closed system wouldn't work. These systems can never reach thermal equilibrium. The question is, what is the reason? Why are these systems special? And the answer is there's an emergent integrability. So I guess for those who don't know what integrability means, that you have essentially an infinite set of local integrals of motions and or conserved quantities, and they do commute with the Hamiltonian. And so essentially this kind of allows you to avoid something like thermalization because of the infinitely many conserved quantities. Now, here in many-body localization, essentially the same is happening, but it's not very obvious. And emergent means in particular, it's like detail dependent, so it's like parameter dependent, and so that's what it means. Emergent means. Now, I'll give you a quick example. Don't do the calculation. I think it just show you what is happening. So this is probably something like the standard model of many-body localization, a Heisenberg chain with a random magnetic field. So here you see like spin operators expressed in Pauli operators, sigma x, sigma y, and sigma z, and I and I+1 are neighboring sides. So think of a spin chain, and essentially this first term, they would kind of allow spin flips, and the third term would be something like a potential term. So this is a strongly correlated Hamiltonian. Now, in addition, there's a magnetic field term in the z direction, and the magnetic field strength, Hi, is psi dependent. So it's a random number, and that leads to, so this is a disordered problem if Hi becomes sufficiently large. Okay, now what people now do is called a finite depth local unitary transformation, and it allows you to kind of go from the original spin, the physical variables or physical bits, the p bits, to some L bits, these local integrals of motions, which we call tau. And if you kind of do this, you get essentially a Hamiltonian of the following form. First term just is kind of linear in taus, then you have a term which is quadratic in the taus. The third term, this is cubic in taus, and so on. It goes like on and on and on. And of course, these consts, these prefactors Ji, Jk, and so they kind of fall off rather rapidly. But to cut a story, don't worry if you don't understand the details. But what you kind of see immediately is that all these kind of operators are tau set. So obviously, tau set will commute with the Hamiltonian, as you see here, and that's your integrability. So you have essentially these many L bits all commute with the Hamiltonian. That's your immersion integrability. And you also see immediately that in this basis, what the eigenstates are, they're just simple product states. Okay, so that's the idea. It's not completely obvious what this finite depth local unitary transformation looks like, but the idea is that you can always derive it. And for this simple case, it's well known. Okay, so this is where the integrability comes from. That's why MBL is a mechanism to avoid thermalization. And just a comment on this, because I know there's some debate. Some people say, I don't believe that MBL exists. This is not true. And this is a principle, an open question, I would say. It just kind of flashed quickly something in a talk I attended a few weeks ago at the March meeting in Chicago. This is a talk by David Hughes, who's one of the leaders in this field. And his opinion This is the same Hamiltonian essentially. And his current opinion about MBL is that, well, here we have for not too strong for weak disorder, we of course in the thermal regime. And then if there's a crossover where you go then into something what people thought is MBL, that's what they call now intermediate MBL regime. That is kind of essentially something that for small system sizes and not too long time scales, not too long for like short times, it looks like MBL. But then it seems as this thermalizes if you go to the thermodynamic limit in late times. But they claim that there's a true phase transition into an MBL phase if you are able to go for very large system sizes, very strong disorder, and you could access the late time limit, which is numerically, of course, very, very hard. So if you're going to, if you're able to kind of access this, that is not really clear, but that is kind of the state of the art, what researchers believe about MBL. Okay, okay, let's go back to time crystals. Historically, the whole thing became interesting in 2016. That is, there were actually two groups independently working on this. One was led by Roderich Mösner in Dresden, the Max Planck Institute, and Zirachi Sondi in Princeton. And they studied actually, now they were looking at driven systems. They realized there's MBL, and then they said, okay, let's look at driven models with disorder. And it is the simplest model you could study in this context, must be interacting, is a transverse field Ising model with longitudinal fields, such it's not integrable anymore. Okay, and then they looked at this as the simplest model, and what they find are kind of these 4 different phases, where PM stands for paramagnet and SG for spin class. And while these yellow and red phases, what you also would get in thermal equilibrium, these kind of green and blue phases are dynamical phases. But these are now truly phases of matter, which only exists in a quantum dynamical sense. So they can only exist if you kind of, these are truly out of equilibrium. Okay, and what they call the pi spin class, that is essentially what we today consider to be this MBL time crystal. We're going to talk about more in the following. Okay, so this was 2016, and then independently, Chita Naik with Bela Bauer and Dominic Els, they kind of looked what they call Floquet time crystal. So Floquet means Floquet systems are periodically driven system. It means that you kind of, we explain in a second what it is, Floquet systems, but it turned out that what they're looking at with a more numerical focused approach is essentially exactly the same what they did. So this kind of blue phase turned out to be their Floquet time crystal. And that is kind of what kind of then was the starting point to say for people, okay, here's a way to really get time crystals. Here's a way to kind of see MBL at work. And you can imagine that a driven Ising model, that is something what is not so difficult for experimentalists. If you have a system where you have already an Ising model realized in some approximation, of course, you might try to kind of experimentally to kind of include some periodic driving and see if you can realize it. So now let me explain what this periodic driving means and what a time crystal really is, what we talk about. So what we need is essentially, we have typically systems with spins, but anything with a multiple degree of freedom would work. But for simplicity, let's think of a quantum mechanical two-state system like a spin 1/2. So we must be able to flip the spins. We need kind of disorder in the problem to allow for many body localization, and we need many body interactions between them. Okay, and if you have that, then essentially you have all the ingredients to realize such a time crystal. So it's a Floquet system. It's periodically driven. That means there's something like a pulse, and it's going to be repeated after a certain time. Okay, it's a periodic driving, or essentially do something stroboscopic. So here, for instance, the whole thing is that you kind of flip the spins. So blue means all the spin point downwards. And then later, after your driving period, all the spins are flipped again. And now all the spins point up. And then you flip again and you go down and so on. So you see that the periodic driving breaks already time translation symmetry, because you do something to the system and then you do it again. That means somehow from the continuous time translation symmetry, you break down to discrete time translation symmetry. I hope you can't hear that, apologies, but I kind of scaffolders outside the building and they make the noise. So I hope that doesn't disturb you. Okay, so the driving period now kind of breaks continuous time translation symmetry with a discrete time translational system or time translation invariant system. And it's like a crystal which kind of breaks the continuous space translation symmetry to discrete time translation symmetry. What is a time crystal or a discrete time crystal? It's a system which has a response which is kind of multiple of the driving period. In this case, it's quite obvious. Think of the spins all pointing downwards and then they're pointing upwards after one period. So the system is obviously not the same state. So you have to go for another period. And now you kind of go back to the original state. So you see that the oscillation period of the system is twice the driving frequency. That's what we call period doubling. Okay, so now what is important to know about Floquet systems is that you can only, measure at so-called stroboscopic times, multiples of the driving period t. Okay. Now, I try to kind of point out a few more important things about Floquet systems. Okay, again, apologies if you can hear the noise. It distracts me very much, but anyways, let's focus. So what you see here is a normal energy spectrum. And like typically you might have like ground states, they might be degenerate, like an Ising ferromagnet, and they can point all upwards and all downwards, for instance. And then you have like typical ground states which build these superpositions, so-called cat states. And all the other excited states, they might be then unordered. Now, this is a normal system. A Floquet system is about time evolution. That means you have not the Hamiltonian to access, but you have actually the time evolution operator, which is e to the I Hamiltonian time. So you look at this object, and of course, now the eigenvalues are also e to the I energy times psi. So e to the I, and you see the energies are now on a circle, on a unit circle. Okay. And a typical Floquet system, which is subject to thermalization, would have these states completely randomly oriented on that circle. So this is how a Floquet spectrum looks like. And now the idea is that a time crystal, a Floquet time crystal, has what is called eigenstate order, namely there are always pairs of states. And to go from one state to the other, you just have to do a global spin flip. Okay. So if you go from here to here, that would be like one pair of states. But of course, a ferromagnet is a trivial example. But you see that it could be any configuration you start with and you flip. And then you see that these states are essentially opposite to each other. So it's just like an angle of pi in between. Okay, this is the idea that you can essentially kind of flip forth and back between such a pair of state, and it doesn't cost you any energy. The system can't heat up. Okay, so that's the idea of a Floquet time crystal, that you kind of port between these two eigenstates. And that would be a way, in some sense, to not violate, but to evade the second law of thermodynamics, in the sense that the entropy is stationary. It doesn't grow. You do not go to a maximum entropy state. Okay, very well. Just quick feedback. Is it okay with the noise in the back, or is it kind of very loud for everyone?
We just have to continue, I think, Stephan.
Okay, okay.
It's fine.
Yeah. Sorry. Again, if I seem to be distracted, it's really because it's super noisy in the back right now.
That's fine.
So, nothing I can do about it, really sorry. No, so let me talk quickly about first generation experiment. As I said before, people realized we need an Ising model, periodically driven, and that's easy to get. At least there's some experiments which have that. And you see like the three most prominent examples. The first two papers, they were actually papered in Nature, like back in 2017. One is about trapped ions. So they had like really these ion traps and were essentially be able to prepare the interactions between the trapped ions, and there's some disorder between them. And it seemed to be just perfect. The other experiment, this was for the Monroe group. Then there's one here about NV centers in diamond by Michael Lukin's group, and they used NV centers. And the idea was that the NV centers, of course, could be randomly distributed, and they talk to each other. There's some effective Heisenberg interactions between them. So this might be another system. And then they were driving both the systems vertically, and it seems to work. Yet another system are so-called NMR crystals, and there were also a bunch of papers on that. And then, of course, it went on. More and more people came up with ideas. And this is really an incomplete list. And I apologize to anyone I've forgotten here. There probably Rydberg atoms array. There were superfluids and lately superconducting qubits. like my talk. And just two of these things I want to kind of emphasize, because this is Australians work from Australia. So there was the idea from Christoph Sascha from Krakow in Poland. And he had this idea of having a BEC, which is like bouncing on a mirror, a driven mirror, if you want. And this kind of the idea was that this could go on forever. And of course, there's no disorder in the system, but nonetheless, so they had these initial ideas and we're working this out and showing, look, this gives essentially the same long time behavior. And it was Peter Hannaford from Swinburne who kind of picked up this idea and started building this experiment. And they kind of very close to realizing this experimentally. And he and his colleagues theory and experiment, and they also did kind of lots of theoretical simulation, demonstrating that they can have very, very long lived time crystals, like several 100,000 Floquet cycles. Yet another experiment which I want to mention are so-called liquid time crystals that is recently set up also in Swinburne by Tapio Simula. And it's essentially water droplets which are bouncing off a liquid surface. And it's really impressive. So if you have not seen it yet, so something I can also, both is really worthwhile looking at. Okay, now here I'm not going to talk about this. I just want to show you that 5 years later, there's really a zoo of time crystals, and many people mean different things when they say time crystals. The only thing which they have in common is that there's something like a period doubling or tripling or so. And it has this kind of, they're usually, and they're all periodically driven, okay? I don't know, go into the details. This is a review article you can look at by Dominic Els and co-workers, and they kind of explain this in more detail. So if you're interested in that, you can have a look here. But you see, it's a long list, and probably it's by now not even a complete list. Okay, so these are the three initial experiments, NV centers and diamond strapped ions and MR systems. And without going into the details either, you just see, if you look at the average polarization or magnetization, essentially the signal of what's your spins doing, you see they go up and down essentially. If they were perfect, they would just go up between 1 and -1 and would keep going forever. Here they all have around about 100 Floquet cycles. And what you see, if you go to the Fourier space, essentially with half the driving period, you get this peak. And that's exactly what period doubling means. So in that sense, these were the first generation of experiments, and people thought, okay, that seems to be a time crystal. Now, let me kind of just focus here on one of the experiments, without loss of generality, the trapped ion experiment. And people then later did simulations on this experiment. And so essentially the experiment, just to be a bit more precise, they used the hyperfine states of 171 terbium, and they had 10 of them prepared. They can prepare initial states, they can manipulate it, they can measure them. How short-range the interactions are is debatable, but nonetheless, it seemed to be a very good system. Now, numerical simulations later revealed that for, say, the ferromagnetic state here in this kind of cyan color, it's kind of very long-lived. You see, it goes like to 10 to the 5 cycles before it becomes smaller. But then if you take another state, like this kind of domain wall state in red, like where half the spins are pointing downwards and the other one upwards, that's the red one, you see that it has a much weaker amplitude, and also it's much shorter lived, okay? And then eventually if you take a random bit string state, where you just have randomly either up or down, that's the black state, it has a much short-lived, this kind of stability is much shorter in time. And that is actually what is typical for what we call today a pre-thermal time crystal. So this is not, seems not to be a true time crystal in the sense that this is a system which doesn't keep going indefinitely. So today, without going into too much detail, what people call, you might have seen this already, pre-thermal time crystals, that is a system which only is exponentially stable for exponentially long times, while a true time crystal would be for, would persist indefinitely. Okay, of course, you could now say for practical purposes, why should I care if this kind of exponentially long time is kind of much longer than the experiments works? And that's kind of the idea that this might be yet a way to kind of have a time crystal realized. Okay, and so if you kind of are very critical, it turns out that most of these early experiments are probably pre-thermal time crystals. Okay, so there's a nice paper by Ippoliti et al. Where they kind of summarize these experiments, and they contrasted it with Sycamore, that's the Google quantum computer, and I took the liberty to add here IBM Q as another quantum computer. And they were arguing that if these on the left are the requirements to experimentally observe a time crystal, long coherence times, you need many particles, you need short range interactions, disorder, and so on and so forth, right? Then you see that all the experiments of this first generation have some problems, while the quantum computer is supposed to be a perfect system to kind of, check all these boxes. And that was then the motivation for them, but also for us to kind of see if we are able to realize such a time crystal on a quantum computer. Okay, so as I said, a couple of minutes, I want to talk about quantum computing. If you had already talked about quantum computing recently, you should maybe let me know now, then I would probably just skip over this. And if not, I will quickly go through this. The idea is really to give someone who has never seen a quantum computer or never played around with a quantum computer, to give an easy idea, a simple idea how this works. Of course, if you're an expert with quantum computers, you can now go and get a coffee and then come back. So now quantum computers, we call them at the moment NISQ devices. NISQ means noisy intermediate scale quantum devices, which points out that intermediate scale only a few qubits of the order of 100 or so, and noisy that really we have large error rates, which kind of are the main obstacle. Okay. Like both, so most of these superconducting quantum computers, the quantum computers are based on superconducting transmon qubits. So this is a whole topic for itself. People working this for a long time, and I'm not going to tell you anything about it. I'm certainly not an expert for transmon qubits, but that's what is hidden behind the quantum computers. Now, for us and for essentially all other users, these quantum computers are black boxes. Okay, so we don't know what is really going on behind the scenes, and all we do essentially is we kind of generate, or we kind of come up with these quantum circuits, and they can be coded in Python, and then we can be submitted, executed via the interface, which is called Qiskit in case of IBM quantum computers. Okay, this is what it's supposed to look like. There's a picture from IBM, and of course the whole thing is to kind of cool this down and kind of connect everything. The chip itself is kind of very at the bottom, and it's kind of rather small. Okay, so now, as I said, let's be very basic. How does a quantum computer work? And how do I do physics on a quantum computer? So this red thing is a qubit, can be pointed up or down, let's say 0 and 1, okay? And then here on the horizontal axis, the time. So we start, they initialize, say they're all in a state 0, and then I can add a quantum gate, which is just really a unitary matrix, if you think in a matrix representation of a vector space or a Hilbert space. And then there are also 2 qubit gates which connect the 2 lines. Like this is what is called a CNOT gate. Come to this in a second. And then at the very end, when you're done with your circuit, you do a measurement and you get an answer. So it's that simple. So let me be more precise. Here X is not just anything. X stands for sigma X or an X Pauli gate. That's just the sigma X matrix. And it flips the spin. So if this was now in a 0 state, it would be afterwards in the 1 state. Then probably the most interesting gate, or the most important gate, is the CNOT gate, the controlled NOT gate. And you see like 1 qubit, that the dot here is essentially the control. If this qubit is in state 0, the gate is essentially identity. It doesn't do anything to the other qubit. But if this is in state 1, it will flip the other state of the qubit. It will flip the state of the other qubit. So here you see what is called a truth table. So this is what it was before. Say if the Q1 qubit was in 0 and the other was in 1, it will be just identity, as I said. Also, it's 0, 1, it's identity, nothing changes. However, if the control qubit is in state 1, like these 2, then it will just flip the other one and you get the opposite. Okay, so you could express this in a matrix, which is a 4x4 matrix, because you act in 2 qubits. And then you see it's essentially here identity, here in sigma X. Okay, but as I said, this is the most important gate. That's the one which makes the trouble for us. That's where most noise comes in. Okay, let's take a look at an example. I have 4 qubits. They're all in the state initialized 0, 0, 0. Here I flip 2 qubits. Obviously, I have not a state 0, 1, 0, 1. I go on, and now I have the C0. And since the control qubit is the second one, this is a state 1, so I have to flip the third one, so I get this state. Okay, now I keep going. I measure, and what I find is, of course, what I have here. 100%, I get 0, 1, 1, 1. That's the answer. Very simple. Very useless so far. Let's look at another example and replace this gate by H. H stands for Hadamard gate. That's a gate which kind of brings the qubit in a superposition of 0, 1. Okay, so matrix representation would be like this. If you start with the 0 state, you get 0 plus 1 normalized. If you start in 1 state, you get 0 minus 1. Okay, and now we do the same game again. We start with this state, we kind of apply, and now the Hadamard gate brings us a superposition. So this one is flipped again. You see like the superposition, the second qubit gives us 0 plus 1. I drop in here some normalization, and then the CNOT gate. Here it doesn't do anything. Sorry, here it doesn't do anything because the control qubit is 0, and here it flips. So it's our final state. And then I measure. But what do I measure? Well, I measure either this state here or that state. So this is really now, I essentially project my wave function, or you could call it the collapse of the wave function, just the way you've learned about this in your first quantum mechanics class. So if you do one measurement, you get either this as an answer or that. It means it's very useless to do one measurement. So you have to repeat the circuit, do it again and again and again. And if you've done maybe a couple of hundred, say 5,000 runs of that circuit, you might get the answer 498 times this one and 502 times that one. Meaning like in a perfect world, you would get like 50-50, and then is exactly the answer what you had here. Okay, so you do this probabilistic, you have to kind of repeat this measurement several times. That's what you're doing. And you can imagine the larger your circuits get, the more expensive that gets. But that's how the quantum computers work. Okay, and now maybe just one slide. I know Feynman can't be missed on this discussion about quantum computing. So it was really him already more than 40 years ago when he gave this famous talk where he envisioned that quantum computers might be actually useful as quantum simulators to solve physics problem we can't solve otherwise. So you can read this up in this publication, and it's really visionary. And essentially, the question is now, I just showed you some simple example what you could do, but you could ask, how can I solve a physics problem with that? And for me, the key insight was actually the following. It's just one example, but I just want to focus on this for a second. So the Heisenberg term, okay, which is essentially this is one of the Heisenberg model is like one of the most important examples of a strongly correlated electron system or a spin system. And so maybe let's simplify, just look at an Ising term, Sx times Sx, okay? And the question is, how do I put this on a quantum computer? And the answer is actually quite simple. There's like an identity, if you wish, and it consists of, if you do time evolution, I have like e to the I Ss, okay? This is now the time evolution of this Ising term. And this can be expressed as two CNOT gates which sandwich this kind of phase gate, which is just a one qubit gate, which is cheap. So you see, if you want to apply for one time step, the Ising operator, the Ising Hamiltonian, then essentially it just costs you two CNOT gates. And with this identity, you get the idea that you can actually look at a whole lot of, like a class of strongly correlated electron problems or their time evolution by kind of compiling these very simple circuits. Okay, so that was for me the insight to say, okay, this is perfect to do what we do anyway, but do it on a quantum computer. So this is the topology of the partition we were using. It has 65 qubits, and we were only using the black ones to have a chain, which is 57 qubits long. So we're ignoring the blue qubits. It's called IBM Brooklyn and IBM Manhattan. And then these are the error rates. Today, there's even a partition with 127 qubits, and there will be larger ones in the near future. But today we focus only on this one here on the left. So if we come to the last part of my talk, now really about time crystals. Essentially, the model we have now to implement is also kind of a driven Ising model. So we directly implement the Floquet unitary, meaning like time evolution operator of the Ising Hamiltonian, and it consists of two terms. The first one essentially is just a global spin flip, as you can see here. So if epsilon is 0, this is a perfect spin flip. All spins are kind of flipped, no matter what their state is. Okay, it does not be a ferromagnet, just any state will be flipped. And then the second term, this is the what we just looked at before. That's the time evolution of the Ising term. Here, not x, but z. Okay, so this is z. Z means just sigma z, sigma z. And we have random couplings, ji. It means for every side, this number is different. Okay, so is this now a time crystal? Well, or maybe even the question is only this term a time crystal because it flips something. But the answer is, of course, that term wouldn't do because there's no interactions. This is not many-body. That's just single particle physics. Now, with that term, we have a many-body system. And the point is, this is still not what we want for the following reason. This is just a fine-tuned point, okay? And a point can't be a phase. So if you're interested in something, it must be robust towards small perturbations, small variations. So we could kind of vary the strength of this kind of box distribution when we take the numbers out, but it's not enough. What we also do, we kind of vary epsilon. And epsilon, if you kind of make this non-zero, it's not a perfect spin flip. So instead of flipping like this, we would just flip to like that maybe. And the question is then, would it still work? Would it keep going forever if you do an imperfect spin flip? But if it's stable, that would be a phase, and it would be a phase of matter, not just a fine-tuned point. Okay, so that's why we allow for imperfect spin flips. Okay, now as a circuit, it's very simple because I explained everything to you already. The spin flips are just single qubit gates. So we start with a bunch of qubits, we initialize them. They could be anything like 0 or 1. And then we just do here essentially this imperfect spin flip for each qubit. And then this is what I've shown you before. That's exactly e to the I, the icing term here, U2. And we first do like all the odd with the even ones, like 1, 2, and 3, 4, and 5, 6. And then the next step, we do like the other thing, like 2 with 3, and 4 with 5, and so on. And you see, once we're done here, that's exactly U. That's the first time step. If you want to do the second time step, then we kind of do the whole thing again and again and again. So that's how it works. It's really that simple. So I ignored so far one point, namely the Hamiltonian I showed you before, or the Hamiltonian corresponding to that time evolution operator is integrable. It's a transverse field Ising model. You can Jordan-Wigner transform it. You get free fermions. And of course, that integrable model that doesn't count. Can't be a true time crystal. Okay. So what we need is an additional longitudinal field or other interactions to kind of break the integrability. And here, the noisiness of the quantum computer helps. So usually the noise is the main obstacle to all what we're doing on the quantum computer. But here we're going to use it to our advantage. So we kind of try to quantify what the noise is in the quantum computer, and it will turn out that we get actually these additional terms, meaning the noise which is there anyway, we can't avoid it. We just kind of use it now as an additional time evolution term, if you want. So this is done technically. It's called process tomography or state tomography, and essentially people have done this for IBM quantum computers, so we knew roughly to what we could expect. So the idea is essentially that you try to fit the noise to something. Imagine you had an additional term, which you would call H addition, okay? And then you would just try to assume there are all these possible terms, and then you fit your noise to that. And then you can quantify them. What you see is that your additional term, which you get from the noise, contains, for instance, an spin flip on the third qubit, or a set term on the third qubit. That's exactly a longitudinal field on the third qubit. That's a longitudinal field on the second qubit, and that's a longitudinal field of the first qubit. You also have more exotic interactions such as sigma x, sigma z, or sigma z, sigma y, and all them together, while the coefficients are not that large, together that's sufficient to break integrability, and we have a truly many-body system. As we said at the beginning, we want to have a generic many-body Hamiltonian. Okay, and here are the results. We measure essentially the autocorrelator time t and average over all qubits. And then what you see, let's start maybe with the blue one. Here, kind of epsilon is very large, such that we really flip only like that. And then, of course, we immediately thermalize the system. And you see the orange curve here, or brown curve, it goes down to 0. It stays down here. Hope you can see that. That's exactly thermalization. There is no there's no initial memory. It's all lost immediately. And of course, if you look at the Fourier transform, it's just a constant. Now, if we kind of take a small epsilon, very close to the case, the perfect spin flip, epsilon 0, regardless of the initial state, you see there is something oscillating forth and back. There are some persistent oscillations, at least for some oscillation periods. And of course, we get then also the peak in the Fourier spectrum at half the driving frequency. Now, you would still say, well, but after 50, 40 time steps, it's gone, it's died out, so it's not a time crystal. And the problem is here, what we see here is really the noise of the quantum computer, okay? It's not physics, it's the imperfections of the quantum computer. Okay, so again, summary, what we see here is no spatial temporal order at all, but for large epsilon. but then small epsilon, we can see the so-called spatial temporal order in time and space, with only a few time steps. And to make sure there's a time crystal, we need to do error mitigation. So what we're doing, I'm just doing this very quickly because I'm almost out of time. So the idea is essentially we kind of do the perfect spin flip epsilon 0, where we would expect that the system kind of keeps oscillating forever. And then we see that even for epsilon 0, we get a very similar exponential decay. And we try to kind of, then we fit this exponential decay. And then we try those qubits who only have a kind of this kind of, let's say, those qubits who are slowly decaying, we get rescaled by dividing essentially through what we're getting through the perfect spin flip, okay? And then the idea is essentially what is left is only what really comes from this kind of finite epsilon. So the kind of this kind of decoherence, which is always there, even for the perfect case, is kind of rescaled. And the result looks like that. And now you see that it's actually staying constant. It's not perfect, it's not at 1. So it's still imperfections in the system, but we stay at roughly 0.7 or so. And you see that it's really going forth and back, caught between the two eigenstates, and it oscillates in principle as long as we can go. This is 50 time steps only. That's when the noise that kills everything. But yeah, that's as good as it gets at the moment. Now, if you want to see the spatial temporal order, you can look here at qubit number versus time. And that's in principle a visualization of thermal noise. Okay, that's thermalization, you see nothing. And here on the left side, you see an example of a time crystal. If it was a perfect time crystal, it would be just all blue and red. And you see some qubits, they're pretty good. They kind of forever blue and red, but others, they kind of almost washed out, as here. So some of the qubits are better than others. And all this has to do with the calibration, which happens every other day or so. Nevertheless, you get the idea that this is what you would imagine, okay? What spatial temporal order looks like. Okay. Let me skip over this and maybe quickly say a word about phase transition, because now for large epsilon, we have this thermal phase, and a very small epsilon, we have a time crystal. And of course, now every physicist asks the question, okay, what happens in between? Is there a phase transition? Can you detect it? And what we're doing here is we look essentially at the, we make use of the fact that the Ising symmetry is broken in the DTC phase, in the time crystal phase, but unbroken in the thermal phase. So it means we can look at the at this Fourier transform of the amplitude of each qubit, and we call this HI. And of course, the idea is deep in the phase, regardless if it's one phase or the other, you would assume that the variance of this number HI should be 0, but near to the phase transition, you have critical fluctuations, and the variance should be finite. That's something we can detect. Here we measure the variance of these fluctuations, and you see that it becomes maximum here, roughly, and that's exactly where we assume is a transition, while deep in the thermal phase, we get 0, and here's not enough space to kind of be able to see, kind of for small epsilon, it's almost 0. Okay, so that would kind of give us a critical epsilon of 0.075, where we have a phase transition between the MBL regime or the time crystal regime and the thermal phase. And finally, we can also look at the average decay constant, saying that the qubit decays in a certain time, and we just do this for every qubit and take the normal average, okay? And of course, this quantity is always finite, but the idea is that in the time crystal, it should not really decay at all. It shouldn't decay at all, only very, very little. And it means this number should be very small, while in the thermal phase should be a huge number. That's exactly what we're seeing. You see that this kind of average number becomes almost 20 in the thermal phase. And here in the DTC phase, while finite, it seems to be almost 0 on this scale. And then we essentially put a line between the first finite point here, and this number is exactly the number we had before. So it's very good evidence that consistently, if you look at these two quantities, we get a transition from here to there. Of course, it's probably fair to say that if you think back of the hand-drawn phase diagram about MBL I've quickly shown you earlier by David Hughes, so it could very well be that this is not the final word, and if people go to larger time scales and larger system sizes, meaning if quantum computers without noise, for instance, or better experiments, then this might change, but like it's at least a first step in this direction to establishing this phase diagram. Okay, so at the end of my talk, I would like to acknowledge, or thank my group. I mean, this work was done only together with Philip, who is kind of here. He did kind of all the heavy lifting, so all the credit should go to him. And of course, I also acknowledge the university and the IBM Quantum Hub, which is established at another university, and that by Professor Hollenberg. And of course, I'm also funding by the ARC. yeah, so I think I just leave the conclusion slide without saying any further. Thank you for your attention.
Well, thanks very much, Stephan. That was it's an interesting topic. We've got a few questions. People are putting them in the Q&A panel. Maybe just while people are formulating their questions, I might just ask one. You showed a nice slide of all the experimental verifications of time crystals.
Yeah.
And I think you made the comment that they didn't have anything in much, were very much in common with each other.
It had or had
because they are very different physical systems.
Yeah. So maybe it's a quick back to them. Yeah. I mean, well, first of all, I really don't want to talk too much about these topics because there are really too many papers. But yeah, kind of first 3 experiments, which we had here. Yeah. Sorry. Yeah. So I mean, what they do have in common somehow, they're really different. You know, in these centers, they're like in diameter, there can be really like thousands, hundred thousands, or millions of these NV centers. Yeah. You can think of them effectively as a spin 1/2 degree of freedom. But of course, where they are, it's completely random. So you have a lot of disorder, and people believe that usually you have something like RKKY interactions or some type of Heisenberg interactions between them. So in principle, that might be not so bad. The question is, can you address initial states, for instance? Can you say, well, one of the NV centers is up, the next one is down or up? And of course, you cannot really, right? So
not in that case, no.
Yeah, and then also measurement, how do you really know? I mean, they're really good at what they're doing, don't get me wrong. It's really sophisticated, but some things can't be done. For instance, the trapped ion experiment, which is really different, is like a quantum simulator. You have these kind of ion traps next to each other. And you know what, you see this in this picture here, these matrix elements, they kind of, they can characterize them. They know how large they are and they can be random. But for instance, it's a longer range interacting system. So I think it scales like, goes 1 over R cubed. And if you do like, if you know about MBL details, you know that it must be sufficiently short range to have true MBL. So if you have long range system, long range interactions like Coulomb, that wouldn't lead to MBL. And I think people believe now that this is probably just too much long range interactions that you don't have MBL at all. And that's why it can't be at best a pre-thermal time crystal, or it is a pre-thermal time crystal.
As I understand it, in that Zhang experiment, there was relatively little coupling between the trapped ions in the absence of any ion motion. Is that correct? Is there a critical amount of coupling, if you like, if one might talk about the phase diagram of this system? If the coupling is too strong, we're not going to get
yeah, there is coupling, but I think the problem is that the amount of disorder which is there doesn't lead to MBL. And in that sense, it's not clear what the mechanism is to lead to the ergodicity breaking, which is, by the way, the problem of most of the experiment, in particular when there's no disorder. People wonder why is it, but it's really about time scales that it might still be that if the driving frequency is chosen properly, you can have exponentially long lived behavior, and you can go to very large times without losing the information. But you need something like MBL to make sure it would kind of persist indefinitely. So, but again, from a practical perspective, you could say, I don't care. I mean, an experiment goes for a day and it's stable. That's good enough, right? Yeah. So it's and I mean, I think the best slide to look at, and it's nicely discussed in this paper, is actually here, where they believe, of course, I mean, they want that the answer is that the quantum computer is best, but they kind of address the problems. So in trapped ions, okay, I didn't say this. Actually, here the real problem is the disorder, but it's not very technical, because if you have the disorder only in the field, the argument is that this might kind of essentially like oscillate out. If they can control the field for each trap, and they can choose this differently. That's how they get the disorder in. But you need really the icing couplings to be disordered for the system to be truly disordered. So there was this argument saying if you have just the fields, the one, kind of the one operator terms, then it would kind of oscillate out essentially, and you wouldn't get a truly MBL system. But look, this is a very technical discussion now already. Yeah.
Well, let's go to the Q&A panel. So the first question is one that you addressed momentarily before from Peter Price. He wants to know, does thermalization in a closed quantum system necessarily require entanglement?
Yeah, I mean, I think I said this before. I mean, like the naive answer would be yes, the entanglement. That's like you would say this equivalent. If it now turns out that someone does research, like maybe mathematical physics research about thermalization, and thinks of a loophole that this might not be true. So I'm not aware of it. So that's why. So just like the naive answer would be yes. But if the person has something else in mind, I might be yeah. This I don't know. So it's too little information here.
So Aiden Kesser, excuse me if I'm mispronouncing your name, Aiden or Aiden. He writes, according to the century-old Poincare recurrence theorem, any closed classical system will go back to its initial state even after thermalization. How do you relate this to MBL? I wasn't aware that it was any closed system. Maybe it is. Aiden might know more about that than I do, but are you aware of this theorem? I have
to admit, I'm not fully aware of it, no. I heard it once before, but I had to look it up. Also want to mention that classical systems, that's an interesting point. What about classical systems? You can have, of course, classical time crystals. Then the question is, can you have many body localization in a classical system? And some people say this is possible. So like I think Norman Yao said they wrote a paper about this. But I'm not sure if this is established. So, you know, whether it needs to be quantum or not.
Yeah. I wasn't aware that in the classical version, I wasn't aware that the motion needed, that the resulting motion needed to be periodic. I think it can return after a finite time to its initial state, and then it might return again to an initial state, but not necessarily in the same period. So to carry the analogy a little bit further, it might be some sort of a time glass or something, you know. So that's kind of interesting. But it's certainly interesting. And of course, that Poincare recurrence theorem has been generalized, if I remember correctly, to quantum systems, and it's quite a simple argument to show that a quantum system characterized by discrete energy eigenstates can return to its initial state after a finite time. But again, I'm not sure whether it necessarily has to be periodic time. That's something that we would have to look up. But that's certainly an interesting subject. Daniel Bergarth points out that in these systems there are periodic driving, and is that a difference potentially to the Poincare recurrence theorem? You've got any comments about that? I mean, do all of these systems necessarily require periodic external driving source?
Yeah, I mean, okay. I mean, what I've been talking about is Floquet time crystal, and that of course implies periodic driving. That is kind of what all these systems have in common. Even the dissipative and the open system, you know, they're kind of also generalized. People have tried to get the dissipative time crystals recently, and used open quantum systems to get it done, even continuous time crystals. But I still believe that what they have in common is that it's periodic driving. So I'm not sure how this would work without a periodic drive.
I mean, I guess it might come down to what you call the system. I mean, if you could include in a dissipationless way without the application of external energy, the driving source, and regard that whole thing as the system, then you're not really driving it externally. I mean, I'm just thinking off the top of my head. I'm just speculating wildly. You know, you might be able to, for example, fabricate a superconducting circuit involving nonlinear circuit elements and perhaps a gyrator to produce a periodic superconducting current, which you can then use to drive the system. I don't know, this might be nonsense. I'm just thinking off the top of my head. But if you could do something like that, then you might in fact have a system, including the time crystal, which you regard as a closed system. But I don't know, that's just the most wild speculation.
Yeah. There's a question about clocks.
Yes, is a time crystal a limit? Is a time crystal a limit cycle in the concept of dynamical systems theory?
Okay, I don't know what dynamic systems theory is.
Is the
limit cycle something like same as a clock, or?
Yeah, I'd have to look it up. I'm not familiar with what Rosemary's referring to there either. Sorry, Rosemary.
But Nadim's next question is about why not, just
Oh, well, there's a mention of electronic circuits. Okay, so he says, Aiden Kessler says, if we're allowed to use external sources, we could easily conjure electronic circuits that generate period doubling. Think of a digital watch. Could you please explain why these systems are regarded as remarkable?
No, but I mean, of course, I mean, say a time crystal is a conservative, robust clock, if you want. So, in other words, I mean, if you take the battery out of your watch and it keeps running, then it would be a time crystal. But I mean, so it's that simple, okay? Yeah,
and it's also probably characterized. Quantum time systems are characterized by the fact that the ground state has some periodic motion associated with it.
Yeah,
in some sense, I think.
Yes.
And I think that's all there is in the Q&A panel. There are a couple of extra comments.
The fifth question was about the noise in the background. Okay.
Yeah.
No, actually,
that's right. Yeah.
Sorry, but
I think we all coped with that. Well, thank you very much, Stephan. It's a fascinating topic, and there's a large number of experiments, and and the potential applications are going to be probably far-reaching, but even more interesting to some of us is what it means for our understanding of our fundamental understanding of the properties of some quantum systems. And I think you've done a very good job of explaining that. So thank you very much, Stephan, and thank you, everybody. And we will keep everyone informed as to when the next seminar is on.
Okay, thank you very much.
Okay, bye for now.